Great. Welcome to Research Jam 26. It's hard to get excited about something when it's the 26th time, but I'm actually pretty excited. We have a full packed schedule today, and every topic just looks very interesting. And we'll start with Gaurav.
Yeah, sure. Thank you. Hello, everyone. Thank you for giving an opportunity to present my topic today. I would like to present like one AI use case, practical use case, which is like email categorization. A little bit introduction about me. I'm currently working as an engineering manager with Thermo Fisher Scientific, and my role is by heart I am an automation engineer writing utilities which can save time and money for the organization. And I have sound knowledge in like cloud, ML AI. Recently started my journey with Gen AI, and like personal front, like I love sports, almost every kind of sports. So about my topic, I would like to present like first, like what is the use case, what is the problem, what we are seeing today is each organization, they are having a support team, and the support team, like if you see strength wise, it's a very small team, but the kind of tickets of what they are receiving, they are being bombarded. Like for example, like crowd strike issue happened, everyone they have reached out to the support team, and they need to answer in a short SLA time period. Similarly, like if there are product-based organizations, they have in turn their vendor organizations. If a vendor is making some changes in the code, that is being reflected back to the client's customers. So now if they are, just consider some scenarios like when they are deploying something new, and the customers, they may come up with some feedback, or they are not happy with the change, or suddenly some dynamic error is occurring, they are raising the incidents. At this time, the whole soul problem starts when this support team, they need to tackle these tickets and answer them in a very efficient and smaller time period. So if you see, sorry, someone is asking some question. Okay. So, 1 second. Let me say right here. Okay. Now, on the right hand side of the slide, if you see, I have captured like what kind of emails we are receiving. Like the customer is saying like, okay, they are not able to log in. It was working till this time period, but after the recent change, they are facing the issue. And since they are not able to the application itself, it's like a P1 issue. When you are receiving the incidents, they are like burning tasks. Immediately, we need to handle it. There are a couple of problems when the help desk team, they are taking care of it. One more thing I would like to highlight here, the emails what the support team they are receiving. Sometimes like the client logo is also there. For example, like if you are receiving an email like from Walmart, Target, Home Depot, you might have noticed that they have logo also apart from the text. So how we can handle it? Like when we are receiving the production incidents, how you can handle it? Production incidents, they are being received. You pass it on to the support team. That support team is obviously like small in strength. They will do some manual triage at their end and pass it to the respective internal teams, whom they feel like, okay, this team, they have recently deployed their changes. Internal team, if they are following agile methodology in the sprint, they will pass it to the developers. Developer will fix the code, will pass it to the QA. If you see here, there are two manual interventions, what the incident is going through. One is the support team, they have to manually triage which internal team this issue could be. And second is the developers, they have to look into the issue. They have to identify what priority they should set, what area of the application this issue might be occurring. So the problem here is the manual intervention. So we have the manual interventions, and that makes it human prone errors. If suppose the support team, they are not able to try it properly at the first end, they might be sending it to the wrong internal team. can we automate it? Can we make sure like the manual intervention is being reduced? And secondly, uh, can we pass it to the internal team which actually should handle this incident? So the answer is yes, and we can automate it using AI. So that is the topic which I thought I will present today. Like this is a practical use case when you are receiving the incidents, and through AI we can actually resolve this manual intervention issues. There are two models, what I will present today. I talked about the emails, the incidents, they are coming as the emails, and email has two things. One is the text, which is the body, which is explaining what kind of incident it is. And second, there is a logo. The first AI model is a text-based model, which I will be talking. This model will read the text, will identify the sentiment. Okay, like the customer is unhappy. He's just sharing a feedback, because if it is a positive tone, it means the feedback is good. If it is a negative tone, you will get to know customer is not happy, facing some issues. So what priority you should set? And secondly, the more you will train your model based on this emails, you can identify what kind of like functionality issue they are talking about. So through text classification, actually we can get all this information. Then why we need a client logo? The key part here is from your text classification, it can give you some idea. Okay, like Walmart keyword is there, so it is a Walmart issue. The problem is like Walmart is in different parts of world. Like it is in USA, it is in Mexico, it is in Canada. How you will identify like, okay, which Walmart customers they are uh, complaining? Because in the text, Walmart keyword is there. It is not talking it is Walmart US or Walmart Canada. At that point, this client logo comes into the picture. The logo for different country Walmart is bit different, which is from the naked eye you cannot identify. But using deep learning ML models, you can classify. So suppose your text-based classification model is saying it's Walmart, you will feed the image to the deep learning ML model. It will also say Walmart, but it's Walmart Canada. So your output will be like Walmart Canada, and that you will pass to the respective internal team who has recently deployed. So we are able to avoid manual intervention by using these two ML models.
Hey, Gaurav, can I ask a question here?
Yes.
You mentioned this client logo detection. Are you also looking at maybe any other images in the email? Do you focus on only the logo or just all images?
Yes, so that's a good question. No, I look for all the images. So what
Mm.
happens, I am using a beautiful soup library for
Mm.
deep linking. So all the links which are related to image, I capture them and just like verify all those images against the saved images. Like my ML model is being trained on like suppose 33 client logos. So what I will do, I'm going to iterate the deep links of images against the client logo. If it's a match, it's a match.
Mm.
Otherwise, pass it on.
Mm.
Now, this iteration is very time consuming, but there is a way we can we can further refine our code. So what I did, if you are like generally the emails what we are receiving, only the client logo URL is different, but other links mostly they are same. So I used to cache them, and instead of verifying against the model, just see okay whether this URL is already present in the cache. Don't invoke the model, because
Mm.
invoking the model is time consuming. It takes time. Your model is residing in S3 or like SageMaker. You are making an API call, you get the response. So caching is one trick what I applied in between to save some time.
Cool, thanks.
Yeah. So as I mentioned, like now I am stepping towards text classification. How I have done it? You have received the email text. Okay, there is a this open source library, beautiful soup, very powerful. And I was just parsing the text. Okay, find by text, and I was getting the text. Uh, uh, just checking okay whether the client name is there or not. But there was one problem. Like I have given the example of Walmart. Walmart is in Mexico also. Now, Mexico, they are using a Spanish language. And if you are feeding your Spanish language to ML model, it will give you like a gibberish output, like that output has no value. So I used one open source library, Polyglot. It checks the language of the email text, whether if it is English, then only you pass it to the ML model. So I talked about sentiment analysis. You are receiving the text. You want to classify, okay, whether it is an incident, it is a feedback, what is the tone. So for that, AI provides one technique, natural language processing. So these are the 4 steps. You have to collect the data. You have to pre-process. Pre-process, we have like remove HTML text. We don't want to feed those to the ML model. They are time consuming. Then there is this part, stemming, or removing the stop words. So for example, like you have different forms of verb, go, going, went. All 3 of them, they are signifying one thing and model does not differentiate it. It's better to pre-process your text, cut down the unnecessary text so that you are feeding only the important keywords to the model. This is part 2. And the part 3 for our use case is sentiment analysis. We want to understand what is the sentiment of the customer, from where he is coming. He is providing us a feedback or what. And the last part is creating the ML model. So for that, I've used TIFF-DIF vectorizer class. So what is the outcome of it? The outcome is like when you build the ML model, what exactly we are looking for. On the left-hand side is the customer emails. They are talking about incidents, they are talking about the new requirements, or they are just inquiring. So whenever that email text is being fed to sentiment analyzer, the output will be like what is the category, what is the criticality of it. It will help the developer to understand like whether they need to take it in this particular sprint or they can just relate to next sprint and like what is the priority. So it helps the product owners, developers to set up like, okay, when they have to actually start working on it. So this is the image classification I was talking about. You have trained your client images. Like for my, like when I was like in my previous organization, there were like 33 clients and I have trained 3,300 images. So when in the email I was getting the image, I was verifying it against deep learning ML model built using TensorFlow and Keras library. Both are open source. At runtime, it was giving me the output, okay, what kind of client it is. So it basically, this image classification model is giving you a peace of mind that what you have received from text classification, that is correct, that is matching with the client logo. So you are building an automation utility. We aim that the output or the internal team whom we have to pass this incident should be correct. So for that verification, image classification comes very handy. So this is the overall flow diagram. Like we have received the email on the left side, like using Beautiful Soup library, just searching for the text name, whether the client name is present or not. Then you are using your ML model to set up the category criticality. Same, and you are passing the images in that email text to your ML model. But before that, the trick here is use the caching, like persist the URLs somewhere. Just check whether like this URL you have validated against the model and it was not a match. So you persist it. Next time same URL is coming, you don't need to make a call. So it actually saves time. And overall, finally, if text classification and image classification, they are matching, you are good to go. Pass it to your internal team whom you have identified. Otherwise, your model requires manual attention. You need to retrain it, because if the emails text what are coming, your model was not knowledgeable enough to understand that. You need to train it with some more data.
Hey, Gaurav, we're at about 14 minutes, so we should wrap up.
Okay. Okay, and this is the
difference.
last part, last slide, like in the real time, how the like when the emails are coming, you can deploy the ML model, generate a pickle file, keep it in S3 bucket, uh, from Lambda, invoke API gateway. So this is the like live flow, how your working ML model can be invoked. So yeah, that's all what I have to present today. Let me know if you guys have any questions.
Thanks. Any questions for Gaurav?
Okay, so my whole code is present here. Like you guys can take a look over this on Medium. So like for image classification, text classification, I've written the code here.
I probably had one question that when you are using this logo detection kind of an approach, or maybe you might have mentioned why you are using it, but are you trying to use that logo detection so that it can eventually help your team or company to figure out what specific client it is, as and so that you can forward those particular queries to a team who is collaborating with that client? Is that a
Yes.
thing?
Yes, you are absolutely correct. So what happens, you have used text classification. Now, when you are reading the email text, you can find the keyword Walmart, Home Depot, Target. Okay. But as I mentioned, like Walmart is in USA as well as Walmart is in Canada. How you will differentiate, okay, which country this email is originating? Okay, generally this is not mentioned in the email text. But the client logo, you cannot see the difference from the naked eye, but this deep learning ML model, they can classify whether it is Walmart US or Walmart Canada email. So that extra piece of information you are adding. And secondly, the logo is confirming, yes, this is from Walmart only. Sometimes like, like you are receiving like Home Depot, I forgot, there were two clients, like both names were there in the email. But using the logo, it gives you segregation. Okay, yeah, absolutely. This is for this particular client. So these are two reasons. And your later part was correct, the flow.
Got it. And also a follow-up question that when these tickets are finally, I mean, let's say categorized into the categories you mentioned, basically multi-classification kind of a problem. So you eventually redirect these tickets to teams. So what I was thinking is, are you redirecting these tickets to whole team, or you are also have tried to redirect to some specific people? I mean, in that particular team, let's say, because each team has some hierarchy, a manager who under whom 3 or 4 people are working. So have you tried to build up to that granular level where ticket can go directly to specific people?
No. Generally, what happens like whenever support tickets, they are being passed on. Okay, it's not related to AI. Whenever they are being passed to the distro group of that team, they are not being passed to some specific person. Either you will have a snow dashboard for like the whole group. Otherwise, there is a distro group for that particular project. So you pass the email to that so that anyone can take a look over it.
Okay, got it. Thanks.
Yeah. Thank you.
Any other questions?
Did you have to train the image classifier yourself?
Yes. 33 clients.
Sorry?
Yes, I have trained it myself on 33 clients.
I see.
Yeah.
Did you have to collect data from all the client images and
No, from Google only. So like they were retail giants like Whirlpool. I was working for a phone insurance company. So all these, they were clients for my company. So 33 client names were given to me, and then from Google, I captured 100 images for each of them.
I see. So that's the only part you train, right? Because the text part you just use the
No, text part I trained. Like if how you will how you will get to know which part of the functionality is causing the error. What I have shown is sentiment.
Mm.
Sentiment is like to look for the criticality, like whether it is an incident, feedback, or requirement, because you want to understand the tone. but what is the functionality which is causing issue? Like, for example, someone is saying login service is failing because of API error. So you want to put that information like when you are passing to the team. For that, you need to train model.
I see. Yeah, I didn't know if you used the off-the-shelf sentiment detection model that's already trained in the library or you trained yourself.
Yeah.
Cool.
All right. If there's no other questions, let's thank Gaurav again.
Thank you.
Thanks for the
Thank you.
presentation, Gaurav.
Sure. Thank you. My pleasure. Thank you.
It's our second speaker, Yu here.
Yeah, I don't see JU anywhere. Maybe he did not join.
We both have emailed him, so let's see.
Great.
He was just emailing me, so it's 18 minutes ago.
Hmm.
It's up.
Maybe he has the time zone wrong. Maybe we can go on with the third speaker and then circle back to JU if he gets here.
Sounds good. So Justin, you predicted right by turning on your camera. So you're next.
All right. Thanks for letting me speak, and I'm happy to share what I've been thinking about. So this is more so like I have an idea slash maybe get some feedback from the community. So let me go ahead and share my screen here. See my desktop. Okay, can everyone see the slideshow?
Yes.
Yep.
Okay, and you don't see like the Zoom stuff?
No.
Okay.
Just see the slide. It's perfect.
Okay, awesome. So basically the out of curiosity, I know this is like machine learning group, but are people kind of interested in like signal processing? I asked because I actually didn't have too much knowledge on signal processing, but out of curiosity, does anyone like is the community pretty like interested in signal processing? I don't know if there's a way to gauge.
Yeah.
Yeah, we just
Okay.
had a PLCT talk that was like very EE heavy. He had a FFT net, wavelet net.
Oh wow. Okay. Awesome. That's great. This is a perfect crowd. Yeah, would love to definitely. This is great that I'm very glad to be able to present or get some feedback. But yeah, essentially like I was interested in sort of this old work on image denoising using wavelets. And so the idea I think is like relatively simple, but essentially suppose that you have some kind of image, and typically in the previous works, and this is from like 10, 20 years ago, right? Classic signal processing stuff, they assume some kind of like Gaussian noise typically. It's a very specific noise distribution. And then it's like given this image and you have this like Gaussian noise, it's like how do you get rid of the Gaussian noise from the signal? And so what they do is essentially do a wavelet transform on your image. And actually maybe I can go ahead and look over here. This is, for example, on the bottom left, you'll see like this is a 2D discrete wavelet transform. You can do this transform. This is a transform with one level, but you can do multiple levels recursively and get these different coefficients. And essentially what they do is like based on some thresholding parameter. So we look over to the right here, you can kind of see how like it gets like zeroed out within a certain range. So essentially coefficients that have a small magnitude up to some threshold t, right, it's going to get zeroed out. And that's how they remove noise. Because the intuition is that like with Gaussian noise, like the sort of the coefficients become small under this transform. But my question is that like, these, previous works, have these like great results on this Gaussian noise, and even they analytically derive like an optimal sort of threshold T, right? But suppose that we don't have Gaussian noise, and realistically, in real life images, we don't know the noise process. And so I'm really interested in, how can we apply wavelet thresholding when to a general unknown noise distribution? And I think there's a lot of work that do this. It's called like blind denoising. I want to make the problem a little easier and say that we're not completely blind, right? I know that there's work like noise to noise that can literally just work with like paired noisy instances. I'm going to assume that we have access to clean images, right? We just don't have access to noisy to clean pairs. Otherwise, we just do supervised learning. And so my question that I've been thinking about in my head is like, okay, we have access to these clean images. We know what should be clean. You give me a noisy instance, but I don't know the noise process. How can I use, how can I find an optimal parameter to disentangle like the noise from the signal? And so one idea I had
And
is
Justin,
that,
can I ask a starter
oh
question?
yes,
So
yeah.
bullet point number 2 says we have access to a distribution of clean images. Are you also assuming you have access to a distribution of noisy images? Like to
Yes,
make noise parameters?
yeah. So you have like
Okay.
a separate two distributions. They're not, so it's not a joint
Paired
distribution.
up. Right.
You have clean distribution and paired distribution. By the way, I only have 2 slides, so feel free to just like this is really more to get ideas from you guys. So feel free to jump in anytime. I don't have that much to go through, but I was just saying like the current idea I was thinking of is like, what if we learn a likelihood on our clean images because we have this distribution? You know, we could just do gradient ascent where our parameter is thresholding, and that's just like, I guess mathematically I wrote it out here, but essentially it's like, you know, just do gradient ascent where it's you're trying to find the t that you're going to maximize sort of like the probability of your thresholded images, you know, being in like this like clean data likelihood. And importantly, we, in this case, we're learning because we have access to clean images, we can also threshold clean images. So we're learning the conditional distribution, or at least I'm proposing to learn a conditional distribution of clean images, conditional on some t, so that way it matches, right? So like if I take some image, noisy image, and I threshold up to some t, I'm going to compare the likelihood under clean images thresholded under the same t. So just to make things consistent. And then I guess at the bottom, just like some visualization, you can kind of see visu shrink. So the left is the original image, the middle is the noisy, the right is what visu shrink does after reconstruction. So they do this thresholding and then they sort of back project or do the inverse transform to the inverse wavelet transform to the real space or the image space. And you can see that maybe they deleted too much signal. And so I think it is important to be able to like find a, you know, kind of like optimal T. I guess here to kind of now pivot over to maybe like passing the mic on, if I'd love to kind of get feedback and ideas from the community. Some things that I would love to, you know, make some ideas on is like, you know, how do we learn this data likelihood? Is there an easy method? I think it's nice in research to start with an easy method. Obviously, you know, score-based generative models, you know, maybe we can get like an upper bound the likelihood. Normalized flows, I think, gives you like the exact likelihood, if I'm not mistaken. But you know, these like normalized flows, I know maybe it's a little sometimes unstable in training, and then I think the score-based generative model, I think it is like strong, but maybe it's a strong hammer. Maybe there's an easier method. The second thing is that I'd love to get some thoughts on is like, is there an easier way to distinguish noise from the signal using these coefficients? Like right now, the machine learning approach of gradient ascent, I think can work, but you know, if you don't have to train a network, then I think that would be better. And then the last thing that I was, you know, another kind of thing to think about is like, you know, with the wavelet thresholding, there are different parts. Like if you see, once again, on the bottom left, the wavelet thresholding is going to essentially create these like 4 categories, like low, 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 high, high, low, high, high. And so maybe considering how to threshold, considering those components separately and thresholding those differently is also another factor.
What are
But
these
yeah,
components? Can you describe these 4 low, 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 high, and so on?
yeah, I think like so basically the 2D wavelet transform is going to take your image and it's going to subdivide it into 4 blocks of the same size. And essentially I think the description of low low means that it captures more like lower resolution features, whereas like high high captures sort of like higher resolution features, and then low high and high low is like a mixture. So like low low, for example, can just be like a downsampled version of the original image, but then like as like high, for example, is going to capture like the higher resolution, finer details. I think that's the intuition. But yeah.
Yeah, it's like low high and high low is more confusing what they would be.
Yeah, yeah, it's hard for me to describe. I'm sure
Like
there
in
is
the
an
X dimension versus Y dimension, is that what this pair is?
well, no, I guess like the images, as you can see, I mean, like they're the same, they're all down, like they're all the same size. It's just like they're capturing different components of your original image. So your original image, if it's n by n, the low, if I'm not mistaken, would be like n by 2 over n by 2, and same with low high and high low and high high. So they're all just like smaller versions of the.
So I think in general this approach seems fine and could work. So what I'm imagining is we have a distribution of clean images, which is like some blob in distribution space. I'm picturing it as like a little Gaussian with some extra little texture. Of course, it's a much more complicated distribution. But let's say it's a little blob in distribution space, and then the noisy distribution is a different one. I'm imagining it's bigger because of the noise you're adding to it, kind of pushing everything out. So let's imagine you somehow learned a model of both the noise-free, the clean distribution, and the noisy distribution. And then you had a new example of a noisy image. One algorithm you could apply would be to just, from wherever it is, march it toward higher likelihood for the clean distribution, and just like kind of go up the hill until you get somewhere that you're happy with. So let's imagine when that would work well versus poorly. Well, that would work well if your noise model was literally adding a small amount of purely Gaussian noise, because then you would know that the clean image you came from must have been nearby, because Gaussian noise is just spreading you out in space isotropically. You could imagine a really weird different noise model, which, in addition to adding Gaussian noise, like flips the entire image in color space. So now actually, if you started here in the noisy distribution, you probably came from way over on the other side in the clean distribution. And so in that world, you might have no hope of finding the correct clean image because you don't have any paired images to like learn that weird mapping. But of course, we're hoping mapping is actually simpler than that. It's a pretty Gaussian or something. So I think this should work fine. And then if you have a model for the distribution that does give you a data likelihood, like normalizing flows or something, then it might just work out of the box. If, on the other hand, you don't, and you want to use something, it sounds like you're proposing a particular simpler model, which is you take the image, you project it into wavelet space, and then you learn a very simple model in wavelet space, which is per wavelet parameter. I don't know what the x-axis is on the right half in these right plots, but per wavelet parameter, you're just learning which regions of wavelet space tend to be noisy images versus clean. And what your plot is showing is on the edges is like the clean stuff, and in the middle near zero is the noise. And so you're doing gradient ascent just per dimension separately, which is an easy function to learn. Does that sound like a faithful representation?
I think so. I think well, I guess I don't know. I haven't thought about like per parameter, but I guess I was just thinking um like yes. So the thresholding T can be a vector. So I guess you can imagine thresholding each coefficient. So in this case, what I mean by coefficient is it would literally be the pixel value of everything in your low or low high, for example. You could threshold each of those differently. So my thresholding parameter would be different for, let's say, pixel 1 versus pixel 2. Yeah, I think like
what's the x-axis of this hard thresholding, soft thresholding plot?
Sorry. In this case, the x-axis is your magnitude of your coefficient. So if your coefficient is really small, then we just kill it. So typically, like noisy coefficients become small after you're doing this transform multiple times. And then y is just what happens afterwards. It's like the coefficient value. Yeah.
So I think then rather than thinking of it as a per parameter, I would think of it as a per coefficient value. So you're taking action per coefficient separately. In other words, you're not considering the entire space of 30,000 coefficients times 30,000 coefficients, some big square matrix of stuff. That's too much. You're just looking at 30,000 coefficients separately and learning an independent, maybe threshold parameter for each. Does that sound like what you're aiming for?
You could do, exactly. You could have like 30,000 T's. Initially, a dumb thing to do is you could have from 30,000 coefficients do 1 T applied universally. But typically, like when people want to get better results, they typically do like different T's for, I don't know if it's per pixel, but at least for components at least, like the low, high versus, yeah.
Yeah, I think it should work. Sounds great. Anyone else have any experience in this part of
I know if people have signal processing knowledge, I would love to get your idea, because one can always go with the machine learning approach, but if you guys have intuition on maybe an easier approach or something, would love to get your feedback.
So the failure case you showed on the previous slides on the
Oh yes,
one of the
sorry, let me go
methods.
back.
Do you think that's just a threshold being too, I don't know, high, or this method just is not the right method somehow?
I think it's a good point. I think like in this case, Bezier shrink does a universal thresholding. So they apply one threshold for all the coefficients. I think that's probably not good. I think maybe, kind of like adaptively choosing a threshold could be better. You bring a good point though, because I think they show in some work that there is like a minimax optimal thresholding parameter. And so that's a good point. That's a good point. My intuition though is that like I think we could improve the way in which we choose our threshold parameter T. But yes, I will keep that in mind. That's an important thing. It's like, what if this kind of killing process is just too, even if for a good T, like what if this killing thresholding process is just not good for eliminating signal, or eliminating noise, sorry.
What do you think is the first experiment you would try, or the first plot you would make here?
So, I mean, what I've done is I, for example, have put in T as a manual parameter, and I guess I could show some images, but basically I have a plot of like, what does it look like if I do different levels of T, and I see the corresponding PSNR. And so if you look at that, like, and I choose the best T, it performs pretty well, actually. But that's me that's me manually verifying, right, after the fact, like, what is the optimal T? We don't have that at inference time. We can't go and like do the PSNR calculation because we don't have the clean version of it. And so I think what I would love to do is to use that as the basis, and then say like, okay, can we come up with the method that adaptively chooses the T, and then see what the PSNR and like SSIM and stuff like that is.
Yeah, sounds great. Would love to see those pictures, maybe if you want next time or something.
Yeah, they're happy to share on the Discord or I guess email. But if there are no other thoughts, just a quick shout out to leadership. Thank you so much for the compute sponsorship. You guys have let me run some experiments, and so big shout out to
Of course.
Good to
Well,
know
great.
that
Let's thank Justin. Thanks for presenting, Justin. This is awesome.
all right. Just, thanks, guys.
Is Jehu here yet?
Nope.
Not yet. Then we can move on with the Nigerian team because since Jehu doesn't want to be recorded, so having him go the last would actually be appropriate. So Prince and team.
Yeah, hello everyone.
Hey, Prince.
Yeah. Moment, let me share my screen. Yeah. Yeah, so hello once again. So my name is Prince and I'm from the Amo Collective Nigeria group. And this is our second time being here. Honestly speaking, I can't believe it's already the 26th research jam. We came here with quote unquote, we have an idea during the research the 22nd research jam. And then we presented our idea to the community. And then today we worked on uh, projects that we presented our idea. And this is like the results that we want to share with you guys. So our project is on the African captions. So we we did a little bit of like research. We wanted to, apply machine learning into various like African contexts or maybe various African facts when it comes to the African context. But then we realized that like there was a problem, and then the problem basically was that the current multimodal AI advancement predominantly focus on high resource languages like the English and also other, languages. But then they basically sidelined the African languages. So this was like one of the limitations when we wanted to implement machine learning into some downstream tasks when we were like doing some sort of experiments. So this like initiated this whole project, and then we decided that we want to, work on this particular project so that we can uh, have more research or more applications when it comes to multimodal AI and also the African context. So two questions that we wanted to answer was, can we extend the multilingual capabilities to vision models? And also, can we create like a high quality data set for low resource African languages from existing data sets and also translation models? And basically, we did answer these questions. Like as I go through the presentation, you'll be able to see that we answered these questions. And our projects, like these are the contributions that our projects, is offering to the community. So a diversified multilingual data set and also context preserving translation pipeline and a multilingual image captioning model. So that's like basically three contributions we are making to the ML community. So we started with data sets. So we wanted to, come up with a data set so we can evaluate and find out like the quality of these data sets, and also when applied to downstream tasks in the African context, as it like what are the impacts going to look like. So we started off by using the Flickr 8K data sets, and basically we chose this particular data set due to like the lightweight and also the practicality of it. So the Flickr 8 comes with 8,000, of course, yeah, 8,000 captions associated with the images. So each of the images, has like five captions associated to it. So we did a little bit of like pre-processing, to just get like one caption per image. And then what we used to do the pre-processing was to use like a cosine similarity index. So we basically calculated the cosine similarity between like the captions, and then basically the ones which were close enough, we randomly like selected one of them, basically to just like avoid bias in selecting, captions, and also to avoid the work of manually going through to select like the captions. And then this idea like related from what we call inductive bias as well, like machine learning models, using some form of assumptions, to like generate output or make predictions. So that's like the motivation behind the pre-processing pipeline, pre-processing like step in this pipeline. And with the translation process, we did use NNLB 200, that's No Language Left Behind, M2M 100, and also Agile Translate. And by the way, Agile Translate is like for commercial purposes. It's not free, when it comes to like the research field. So these are like the three um, machine translators that we use to translate our data sets. So after the translations, we performed like quality assurance or qualitative analysis to ensure that the data sets that we for the translations that we generated are close, to what we expect. And then we relied on like two main processes. So one is like an automatic evaluation or automatic like quality analysis, and also human evaluations on the data sets. And then with the automatic evaluations, we did use like the cosine similarity again. So we compared the cosine similarity between the original caption and also the back translated caption. And then basically there was like an issue over there. So when it comes to like these machine translators, they do well translating from like English, being like the source, and also the targets being like another language. However, if you try to back translate them, into English, it's loses like some form of some sort of context in there. So that's one of the major challenges we face. So we did get like should I say, yeah, created to like a good, data sets. But then it was still not enough, just automatic evaluations was still not enough using the cosine similarity. So we came up with something we called a heuristic like filters. Basically, we set a threshold, and then we use this threshold to like filter out or weed out translations which are basically not good enough to be considered. And then basically how we did this was we have like a small community among ourselves, and then some of us do are native speakers of some of the languages that we considered. So we manually evaluated like samples of the translations, and then we realized that translations below the 0.53 threshold are not good enough to be considered. They totally like lose their context during the translations. So we decided that due to like this observance, we are going to ignore, or we are going to eliminate translations which has cosine similarity, or cosine similarity scores below 0.53. And then after filtering out or weeding out the bad translations, we realized that like the translations that we have used have like quality similarity index score between 0.53 and also 0.59. We also went ahead to add a human evaluation, and then this step was like a little bit difficult because of like the resources that we need. Because we basically need humans to be able to like perform these evaluations, and that's also like one of the hurdles like we encountered during like the process. So at the end of it, so like we
Prince,
perform.
can I ask a question here? Can you go back
Yeah,
one slide? What is the maybe I missed this. What is the cosine similarity OR and BT?
yeah. So the cosine similarity, the OR basically means the original caption, and also the BT is the back translated caption. So the original caption is the caption in English, and then the back translated caption is uh, the English caption, which was translated into like a target language, let's say Yoruba, and then it was now back translated into English. So it's like English to Yoruba, then Yoruba back to English. That is what the BT stands for.
So I'm wondering, in cases where we don't have a lot of data from this language, what if the back translation is just bad because the back translation model is bad?
Yeah, so uh, that's like one of the things that we observe, that basically these models are able to perform the back translations really well, as like compared to what we thought like it could do. We basically at the beginning of the experiment, we thought that it was these models would be able to translate into the target language, and also back translate into the original, language. But then after this particular process, we observed that it's poor, when it's trying to back translate into the original language. So that is why we implemented the heuristic filters to read out like the translations, or like translations which basically lost their context when we back translated.
So that makes some sense. Maybe back translation or translating back to English is maybe it's relatively easier. But I worry, what about cases where you have a specific concept or phrase or word in a specific language that's very hard to translate, and the translation model doesn't understand that, and then the back translation ends up very bad, but actually that's one of the most valuable points to include in the data set if you could. It seems
Yeah,
like there's some tension here, maybe.
yeah. Uh, so we did realize few of these things we are talking about. So some of these things we realized were when the model was like finding difficulty translating like idiomatic expressions in these sentences. So in cases like this, the translation is not going to be good enough. So we ignored it. So we are yet to like find out what we can do in order to like preserve or yeah, in order to preserve like the context or in order to include these kind of phrases when we are translating. So obviously the back translation is not a good idea. So I think in the future, these are some of the things that we consider.
Cool. Thanks.
Yeah, great. So yeah, we did perform like analysis on our data sets, and then basically on my left is a distribution of the average word count per language in the AFRICAPTION data sets. That is data sets that we worked on. And on my right is a plot of the average human score per language with error bars denoting the standard deviation. So on my left, like there's been like a perceived like performance on models, when compared to the average word count, in the data sets. And then basically this denotes like reasonable, like this shows like a reasonable standard in a sense that there are no like captions which, are out of distribution and also like not overly verbose or like something like very briefly, translated. So like the chart on my left shows like a reasonable average when we want to like perform some um, max with it, like we'll be able to achieve a good performance. Basically, that's like what perceive average word counts of the research community like looks at when we want to consider things in this case. And on my right is like the responses that we receive. I mean, the human evaluation responses that we received. So we receive like a good number of our responses, and then that like range from Yoruba and it's went on all the way to away. So what it shows that is like most of the um, evaluators like review the translations to be having like a score between 6 and also like that of an 8. And then basically how we did this was we sampled out a few of translations in our data sets, and then we basically evaluated it like due to the adequacy of the translation. So what I mean by adequacy is the translation like conveying the message in the same message in the original caption. So forget about like the direct translation. All that we focusing on was that is it able to like convey the same message as it is in the original caption? And then that's what we use. And basically we use like a Likert scale from 0 yeah all the way to 10. So 0 being bad and then 10 being good. And yeah, for Yoruba, most of our evaluated did say that translations were like yeah, okay to like good. Um, and then with the standard deviation, which was like 4.3, I mean, the standard deviation, the average standard deviation was between like 2.5 to like 3.0. So this like basically means that the model was able to other translations that were good enough to be viewed. And because yeah, it conveys like most of the contents in the original version. Um, yeah, so we went ahead to train a model or yeah, an image captioning model with our data sets. And then basically what we used was like the Seglet vision encoder and also the NNLB like decoder. So basically these are the two major models that we considered in the second caption model. And what we did was that we joined both models using the Hugging Face Vision encoder text decoder class, and then we modified it a little bit to suit our particular text. So we did like training twice, and that's the first thing that we did was to do a selective layer pre-training for 40 equals. And then what this selective layer pre-training was that we pre-trained the linear projector and also the final layer of the Siglet vision encoder. And that's what we trained or pre-trained for 40 epochs on the English captions. And then we did fine-tune it on the other African languages for 10 epochs after the pre-training was done. And then these are like um, the resources that we use, and also the batch size, batch size of 16, and also L4 GPU, thanks to ML Collective. And after the training and everything, we did make some evaluations. We did do some evaluations. And basically, we compared the references to the predictions generated from the model. So on my left is the target, starting from my left on the table is the target's language. The next column shows the reference, and then on the right is the prediction generated by the model. So if we check the first one, you can see some text highlighted in yellow. So that is like the difference between the reference and also the predictions. The same goes to American and also Hausa. So naturally speaking, or naturally speaking, we would say that model is able to perform well, and then it can be used to uh, perform the data set itself can also be used to perform some other tasks when compared to like state of the art um, models that we have specifically for the African context. Yeah, so right now, our next step, we've submitted like our paper to African NLP. It's currently under review. And next step in the next step in the experiment is that we want to compare the automatic translations with the human evaluations. So we've like observed like the qualitative analysis of the translations. So we've been able to compare the automatic evaluations with the human evaluations. That is like qualitatively. So now we want to also add like a quantitative analysis. There's something like something that we can use to like compare the automatic translations with the human evaluations, and then to produce like a quantitative analysis on the entire project itself. And after this particular step, we want to submit to POLEM or EMNLP. And then after everything, we want to scale the project, and then we'll be utilizing like the insights learned during this experiment. So in actual sense, this project started as a proof of concept. So we wanted to find out how like the community, when it comes to like the multimodal applications in the African community, like the impact and also like what the current status of it's in there. So basically that's what this project was about. So we are going to utilize the insights and also like the things that we've learned throughout this project to scale or to provide like a series of projects where we'll probably be working on like instruction tuning models and other like vision language models which can be integrated into the African context without any loss of like cultural representations or anything like that. So and we've done our best to perform like the experiments and also analysis on the uh both on the data set and also the model as well. But then we want to also get the community's feedback on it. Maybe some things that we can improve or some analysis that we can perform to further like validate our model and also like our data sets or the entire research in general. So that is why we wanted to present here today. And this project wouldn't be possible, without our one and only mentor, Ms. Caterina. We want to thank her and also like thank her again the second time for the movement and also willingness to help us succeed. And of course, we can also not go without thanking them of NOC for the complete support and also for the feedback we've received so far from the other community members. We also want to thank like MLC community, that's particularly the Nigerian community, for helping us with the human evaluations. And finally, I want to thank my team members for not giving up on this project. So that's all we have for you.
Great to hear this update, Prince. Any quick questions? We're a little over time, but we can maybe take one quick question if anyone has one.
So on the training, the model training part, do we freeze the image pipeline, or you train them together?
Yeah, we train them together. So we freeze some of the models, some of the layers, So in the Siglet vision encoder, we froze all of the layers except the linear projector and also the final layer. And that's where we perform the pre-training using the image. Uh, yeah, and then when the pre-training was done, we did like the entire tuning using the other uh, using the other languages. That's the other African languages.
Yeah, I think it makes sense for the image part to be frozen somewhat, but until the last linear projection, because you want to project into a different language. That makes sense.
Sorry, come again.
I'm just saying your setup makes sense to have some
Okay.
part of the vision encoder frozen. I don't know if when you
Yeah.
fine tune, you do train everything though, right?
Yeah. I mean, kind of like a linear program where you just froze some parts and then just fine tune the other layers.
Mm.
Any other question?
If no more questions, let's say thanks to Prince again, and also Prince, a number of other collaborators on this project are on the call here. So thanks to all of you for presenting. Congrats on the great work, and fingers crossed for the kind of current review process.
Cool. Our last speaker won't be recorded, so we're gonna stop recording here. Those on YouTube, see you next time. Stop.